We're not building spaceships here. What is all the fuss about? Is a comment that was left in one of the previous videos. Totally get the sentiment. We're a cycling channel. Why on earth are we making a massive fuss about greases and bolts and torque wrenches and equations and mathematics? And I totally get it. And this all comes from one, we want to do a really good job, and we operate at the top end of the market, the high performance end of the market. And what we're doing doesn't necessarily appeal to everyone. But at the top end of the market, things are different. This is not aerospace. This is not automotive. This is not civil engineering. You know, all those rules and regulations that all those engineers have to abide by. In cycling, we only really have ISO 4010 and we have some UCI guidelines as well. And that's it. And that's the problem, because it's also a very competitive sport, not just in terms of winning races, but also in terms of winning your hard-earned dollars. It's a recreational leisure pursuit. We know that when we buy a cycling product at this top end of the market, we are buying it on weight. We all know that's the most important thing. The price, we're buying it on the aesthetics, how good it looks on our bike, the obscure performance guidelines that may be touted in the marketing, and then maybe some fame on like which famous rider is using it. Probably next in the list is durability and safety. Be honest with yourselves, that's pretty much how you buy your cycling stuff. So the problem with that is that the engineers in these cycling brands are then given the brief. Like, I need you to make this product as lightweight as possible, lighter than all our competitors. I need it to be as cheap as possible for maximum profit, and obviously to actually sell it. There's no point having a product out there that's 3 times more expensive than your competitor. And it just needs to pass the test. It needs to pass the ISO drop test. It needs to pass the ISO, steering test, whatever that test might be. And if you're an engineer, you will learn over time how to hack the test. You will learn what's the minimum required amount of material to pass the test. And that's kind of what's happening at the top end of the market. We all like pushing the envelope. Things like factors of safety or margins of error, etc., that you're familiar with in other industries and are an essential part of that engineering, just don't really exist in cycling. They get eaten up by that drive to save 20 grams, because that ultimately is what will sell the product. There is a little caveat to this, and that is, here in the West, an engineer still has to abide by, certain best practices, etc. Let's say, for instance, something that they designed broke fatally or catastrophically, and someone had a really bad accident, and they had to go to court and justify their design decision to a judge. And the prosecution was saying, could you have foreseen a situation where the rider hit one pothole and then instantly hit another pothole, and that caused the component to fail? Or did you just design it purely to pass the minimum requirement in the test? Now, I think most engineers would probably build themselves in a little bit of factor of safety, which is what we tend to see in Western designs. So that is why assembly of these products is critically important, because there really isn't such a thing as a massive safety margin in there. So we're going to go deep into all of this, because it really can change a lot very quickly without you necessarily realizing. And to prove all that, I'm going to try and get into the theory. Now, in the last video, I introduced this equation for you. Torque equals friction of the bolt times the dimension times the force. So when you see on your stem, it's written 5 Newton meters, and you see that the bolt has got a bit of that blue pre-applied thread lock, and you're going to take your torque wrench and use it properly by holding it by the handle, just as your torque wrench manual says you should, and has been calibrated to be used in that way, and you tighten it up properly under momentum and you hear the click. That is perfect. The clamping force is correct. So with this equation in mind, let's just fill some gaps in and put some numbers to this. That's something that we didn't do on the previous video. So we have T, 5 Newton meters. That's written on the side of your stem. We get that. K factor. For now, we're going to go into this deeper in the video, but for now, I just want you to believe me that a bolt with a patch on it like this got a K factor of 0.2. Then the dimension of an M5 stem bolt, because we are working in Newton meters, we are working in meters, so this is going to be 0.005 for 5 millimeters. And effectively, all we need to do is just rearrange this formula, so we get to F equals T over K times D. Now fill those numbers in, and so we have 5 Newton meters over 0.2 times 0.005, work all that out, and it comes to 5,000 newtons of force. If you're still with me, well done. The next thing to do is I want to prove the point by showing you the mathematics behind it. Now, I'm going to use this as our case studies. This is a data carbon bar on a Shimano Pro stem. It's standard 31.8 clamp and it has 2 bolts. So this particular lightweight stem has a little clasp mechanism here, and there are 2 M5 steel bolts holding this in, which have been pre-thread locked, and the sign there says 6 Newton meters. So in factory settings, what is it that we're looking at? Let's work it out. Okay, let's try and find F, force, for this particular handlebar setup. So we know that the K factor is 0.2, and we're going to multiply that by the bolt diameter in millimeters, which is 0.05, and we are going to divide that all by the torque, which we know to be 6. We can hit equals, and we get 6,000 newtons. Right then, scenario 1, we have taken our bike apart, we have serviced it, and we've discovered that that little blue patch is virtually non-existent. There's just the tiniest little trace of it, and we want to replace it. And we're going to choose a Loctite 248, but we're going to be vigilant because we're dealing with lots of carbon. Is the K factor going to be the same? So we have the Loctite technical data sheet here. Now, this one is only available on the consumer website, but Google it, you will find this document somewhere. Not all of the consumer ones have the K factor on. This one does, and it quite clearly says here that the tension with product is 0.19. Okay, making this small change, we have 0.19 times our 0.005 divided by our 6 Newton meters equals 6,315. So just making that tiny change has already added 315 newtons of force. Now that is probably well within our factors of safety, no matter what it is. But what happens when we go in to change it? Let's say rather than replace it with Loctite, we're going to use an anti-seize. An anti-seize can come in a couple of different types. This is a true anti-seize by a company called Weicon. We're going to cover this when I talk about my greases. We'll tend to use this in situations where we're dealing with more exotic metals. So think titanium, stainless steel, that sort of thing. It's incredibly expensive and it hasn't got amazing washout properties, but you are switching that against the benefits it gives you for cold welding. Now, if you just want pure washout performance, we stick to that Maxima assembly grease. If you can't get that, a few of you said you're struggling to get it, we can use this as well. This is Peerless OG2 calcium sulfonate grease, a very thick one that doesn't wash out very easily, but it's not a true anti-seize. It still works like an electrical insulator rather than something that's just going to slow down that galvanic corrosion property. So we like using that. It means that we don't have any heavy metals in our workshop. Again, refer to the previous video. Now, both of those I know to have the same K factor, but where do we find that? Well, we go to the manufacturer's technical sheet, and here from Weicon is their technical data sheet. And right the way down here, it says coefficient of friction on a thread 0.13. So what on earth does that monumental change do to the amount of force exerted on our handlebars? So let's plug that into our equation, and we're going to have 0.13 times 0.005 divided by 6 is going to give us 9,230 newtons. So that is significant increase, well past any sort of factor of safety, and we are now in the position where we are crushing carbon. We're not quite at damaging bolts, we'll get onto that in a second, but that is a mind-blowing increase, I think you'll agree. But it might not stop there, because you might have noticed that a lot of the time in cycling, other YouTube channels, etc., or the training course that you went on said, actually, when you're using titanium or exotic metals, you should probably use a nickel lubricant. Now, this gets really complicated. So just to bring this up, you've really got to be careful. When you buy lubricants from the cycling industry, they very rarely have their safety data sheets and their technical information. Something that drives me absolutely insane, because theoretically, if you're a pro workshop, you should not have anything in your workshop that does not have a safety data sheet attached to it. So many cycling products don't have that. Anyway, so this is a printout from a website from a cycling brand that does not have safety data sheets, and their nickel grease describes it as this. It's to blow your mind. Anti-seize is engineered for aerospace standards. Remember, we're not building spaceships, and it proudly boasts that it is suitable for service up to 1,426 degrees centigrade. So if you did crash your bike into, I don't know, the sun or a blast furnace, at least your grease will be okay. The rest of you might be vaporized, but anyway. And it also boasts copper-free, lead-free, no PTFEs or PFAS. Brilliant. But dig down into the details and it says with a superior nickel-based formula. Now, go and look at some of the control of substances information, and nickel is probably one of the worst things of all the things that I have just put up there. It is now a suspected carcinogenic and is really not very good for your fingers. And also that grease is slippery as hell. It's very watery, it runs off and really does not stay put unless you're in extreme high temperature situations. Now, I did find the similar grease from probably the brand that supplies it, because cycling brands don't make their own greases. They're normally repackaging more commercial things. So we went and found the actual technical data sheet for a nickel grease of similar properties. And this has given us a coefficient of friction of 0.086, a significant reduction. So let's run those numbers and see what the hell that would do to your carbon handlebar if you didn't adjust your torque settings. So with our nickel grease divided by our normal bolt torque gives us a staggering 13,953. So we have more than doubled our preload force just by reducing the friction of our bolt. And that is a catastrophic failure. If it doesn't destroy itself in the workshop, it will not take long before some shock loading when you are riding it is going to bust that apart. That is way beyond, I think, what any engineer would build in as a factor of safety. So reducing your torque settings is really important. I hope I've demonstrated that. But by how much? That's the big question. You can run these sums back the other way. So let's do that, but let's go back to something a little bit more sensible, down to something with a coefficient of friction of 0.13. And we have 3.9 Newton meters. So we need to reduce our torque down to 3.9 Newton meters. So that should give us 6 minus 3.9 divided by 6 equals. And well, that gives us 35% you should have lowered your torque settings by. So it goes to show you probably always do your maths, go and check your K factors and do it properly rather than doing rules of thumb. Now, I will let you guys work out whether that would have busted through any suspected margins of safety. I suspect it probably get very, very close. But what I do want to do next is to work out not just the danger of crushing carbon, but actually what is the danger of we actually start breaking bolts. For that, we are going to need to consider two bits of safety information that you get when you buy a bolt. And when you go to the spec sheets of a bolt manufacturer, you'll see two bits of stats. You'll see the yield strength and you'll see the ultimate tensile strength. The yield strength is when the bolt is going to be deformed, and then the ultimate tensile strength is when we can expect it to shear and snap. Now, that measurement is actually measured in megapascals. So we need to take our newtons and turn that into megapascals. And the way we do that is that we need to find out the diameter here. And the thing to do is really try and look it up online. But for an M5 bolt, for instance, it is a pretty standard 0.8 millimeter thread pitch. So we can normally assume that for a 5mm bolt, an M5 bolt, the actual central cylinder, the bit that doesn't have any threads coming out of it, is going to be about 4.2 millimeters in diameter. So what the equation for that is pi over 4 times the diameter, 4.2 squared equals, and there we go, 13.85. So to find our megapascals, we just times the force, which we know to be 6,000 in ideal handlebar, divided by our 13.854, and that will give us 433 megapascals. Now, for a steel bolt, that is well within range for the standard stuff that we see in the cycling industry. So you'll see stamped on the end of bolts a little number. Now, in cycling, we tend to only see 8.8, 12.9, but you can get 4.9. So on a very low quality bolt, we've almost certainly got very close to, if not exceeded, the yield strength of a low quality bolt. Now, that is assuming our torque settings are exactly right. Okay, let's have some fun here with some sort of probable hypotheticals. Let's say this is your handlebar setup. Really proud of your bike, you're going to treat yourself to some titanium bolts, and you've been diligently watching YouTube channels and have brought yourself some nickel grease just for that application. And let's say you've got a torque wrench that you bought 5 or 6 years ago, you don't use it often, you assume that it's okay, but no one's ever taught you how to use it properly, or you do it up under momentum and that sort of thing. And let's say you exceed your Newton settings by 1, let's say you go to 7 Newton meters. What on earth does that do to our situation? I think it's kind of believable. We've definitely seen it play out. So let's run those sums. So we know that our K factor is going to be a staggeringly low 0.086 times our bolt diameter, and then divide that by 7 this time, going to give us 16,279. Wow. That is a fairly big number, considering that we started this whole exercise at 6,000 Newton meters. We've exceeded that by 10,000 by changing relatively little, just bolt torque by 1 and changing our lubricant. Okay, but what if you've now got those fantastic new bolts, and are you actually going to break them? Well, let's run that sum. So we copy that result down. That's in newtons, remember, and we need to make this into megapascals. So we did that sum earlier, 13.85, and we now get to, and this is megapascals, 1,175 megapascals. Now, this is the tech sheet from Tire Bike, somewhere where you might go and buy your M5 titanium stem bolts. And in there, you'll see that the yield strength is 870 to 925. So we have definitely exceeded our yield strength. That means the bolt is going to be stretched, deformed, and not do its job properly. We've also just exceeded the ultimate tensile strength as well, over 1,000 megapascals. Now, arguably, due to some sort of probabilities, a bit of luck, and maybe some built-in factor of safety, that bolt might just stay together. But only just, it's probably only a fairly big shock load away from failure. Okay, I know what you're all thinking. Would this actually happen in practice? Would my mechanics instincts take over, and that white knuckle gauge, if you like, stop me from over tightening a bolt? Well, in my experience, no. Because all of this does come from experience. Back in the day when I was into lightweight and everything, and I wanted my bike to be as light, I made these mistakes. I've snapped bolts, I've crushed carbon. And when I became a pro mechanic, I swore to myself that I'd never do that again. And I wanted to understand the mechanics and the engineering behind why it happened. And this is why I've gone down this voyage. The cycling mechanic training you get is totally inadequate. They don't cover this sort of stuff in SciTech and City and Guilds at all. But it's vitally important, one, that you understand the chemicals of the greases that you are using, the coefficients of friction, what impact that has on your torque wrench. And if you don't use your torque wrench properly, the last video, I was shocked at the amount of so-called pro mechanics who were insistent that you didn't have to hold a torque wrench by the handle. That is how they are calibrated. You have the length of the lever, the internal friction of the mechanism, and it is calibrated for you to use it at the handle. Don't believe me? Go and look up the instructions in your torque wrench. Now, if I am wrong, please link me those instructions, but I'm pretty sure that your torque wrench will say use it by the handle. And what you're seeing here is if you decide to go off script as a mechanic, that you decide to change the Loctite or the lubricant, the bolt type, torque settings, then you very, very quickly run into a pretty nasty situation. Now, the best case scenario is that this happens in the workshop, that you over tighten the bolt and it shears, or you over tighten the bolt and you hear the crack of carbon, you back it off and you're like, oh, I've seen it. So that best case is that you now have an expensive bill on your hands to replace it for the customer. The worst case is that everything looks okay, but it's only one shock loading away from a catastrophic failure. Hit a pothole, you lead into it heavily, you get out the saddle and you load up the bars, and all of a sudden you are increasing the force way beyond what the design parameters ever were. And then you have a problem. So this video isn't about scaremongering. This video is about, please go and do your research, go and look up the safety data sheets, and also an appeal. Like, if you're going to go and buy a cycling branded grease, like, send an email to all of those brands that you're considering buying, and say, where's your safety data sheet? Where's your technical information? Give me the information. If it's not there, don't buy it. It's as simple as that. We've gone down a voyage of trying to find high performance greases that we know that we can go and look up the data. We've got the safety data sheets on file in our Kosh folder, and that's how you run a professional workshop. Buying cycling greases where that information isn't available, it's just not the way to do it. Okay, over to you guys in the comments. I congratulate you if you all made it to this far in the video. Seriously, well done. It's a pretty heavy one this time. Again, put your comments down below. Go and run the sums. Go and do your own research. Go and find what greases. Go and find your K factors. Tell me what you have learned from your own research as a result of watching this video. I'm really keen to see what you come up with. Thanks very much for listening, everybody. We'll see you on the next one.